Now let's consider another potential difference for one of our symmetric charge distributions. So let's take a very thin spherical shell of charge plus q and radius a. And let's take an outer shell with a charge minus q. Both of these charges are spread uniformly over these shells, and that's a radius b. Now, once again, from our Gauss's law calculation, we know that the electric field is 0 inside and outside this configuration, and it points from the positive plate to the negative shell. And from what we expect that the potential function will be higher on the positive as opposed to the lower. So I want to do this calculation in the following way. So let's take the potential difference between where the positive charge is and where the negative charge is. So I'm going to integrate from, I'm going to integrate from the outer plate, outer shell to the inner shell, and I'll choose a path, once again, that's going to go straight. So this is going to be my path, divided up into a bunch of pieces, and I'm going from, now I'll go from the plate, the outer one, to the inner one, and I'm just denoting it by the radius of E dot ds. So once again, we have to set up this integral, and recall from Gauss's law that when you're outside a uniform shell, it looks as if all the charge were at the center, and we found that the electric field in the region between the plates as a function of r is just k charge on the plate divided by r squared r hat for the region a less than r less than b. Now, here comes the interesting thing. Again, we'll write ds in a coordinate system in which our r hat vector is spherically outwards, the radial vector spherically outward, and we write dr r hat. Now, many times people will be tempted when they see this path to put a minus sign in here. But remember, dr is just a quantity that can be positive or negative, determined by the endpoints of the integral. And so what we get is that v of a minus v of b is minus the integral from r, we're going from b. Let's make sure we have that right. We're going from the outer shell to the inner shell. And now the dot product of these two vectors is positive. R hat dot r hat, positive quantity. And there's a minus sign overall on the outside. So we have a one-dimensional integral representing by taking a path just in one dimension. And this, again, is a straightforward integral. dr over r squared, the integral is negative 1 over r. The two minus signs cancel. So we get kq over r squared over, putting the endpoints here, of 1 over a minus 1 over b is this potential difference, the a minus vb. Now, let's just check that our calculation is correct. What did we expect? There are different ways to think about it. The electric field points down to lower potential, so we expect this surface to be at a higher potential. It's a positive charge, so that kind of reinforces that idea. And if a is less than b, then 1 over a is bigger than 1 over b. And so we see, as we expect, that the potential difference here is positive. And indeed, our inner surface is at a higher potential, and the outer surface is at a lower potential. And there's the case of two concentric spherical shells that have opposite charges.